Welcome to the presentation of basic power system. So first of all, I would like to mention the definition of power. So is the rate change of energy with respect in time in terms of voltage and current. So typically expressed in watt. So in DC circuit, the power is normally expressed in P equals VI, that is a voltage multiplied current, and there is a watt, the unit is watt. But in AC circuit, there is a three different power. It's called active power expressed in watt, and then there is a reactive power expressed in volt ampere reactive, and then the apparent power is VI, this is just unit is a volt ampere. So later on we will see the difference. What is the basic difference between AC power in AC circuit and the DC circuit? Now let us see the power in a single phase circuit. Just a basic. Yeah, it's just called instantaneous voltage. Here A represents the point at any node, because if we want to measure the voltage, for example, voltage is the point A and this is the point neutral, then there is a voltage difference between 2 points is known as BAN. It's a sinusoidal function, is the maximum value, whereas the current represents there is a theta lagging, so there is a phase lag of theta. So and the power can be expressed as P equals VI. So now let us see in the three different scenario in AC circuit. This is for resistive, this is for R, and this is L for inductive circuit, and this is C for capacitive circuit. Here we see that we know the voltage and current, there is no phase difference between this, and so the phase lagging, the theta is 0 here, and as well as the power factor. Later on I will talk about the power factor. Is the power factor 1 is called unity power factor, and here there is a, for inductive circuit the current is lagging. We see that the black one, whereas all the three graph, the reddish for the voltage, this is a sine wave, whereas the current just lagging this value. If I just extend this here, so is the theta, this is the theta, so this is the lagging. In inductive circuit, typically current lags the voltage, and it is called the lagging power factor actually. So, and here in the capacitive circuit, we see that the voltage curve remains same, whereas the current curve is just to follow the cosine wave. Is just a leading one. If I just extend in the back, then we see here this is the theta, or this is the theta is for leading, then we have to add a plus sign here. So here you see that it's a leading power factor. Now see the graph here. So it says that the current is a reference one, in the phasor diagram current is reference. So if I express in the polar form, then this is I magnitude, and this is the r theta. So this is the theta, here is the phi, actually the theta. So here voltage is leading and the current is lagging. So this phasor diagram is for inductive circuit. This is for inductive circuit. So lagging, actually it's always expressed by the nature of current. So here inductive circuit, the current is lag here, and yeah, so because in all the parallel, because all the home appliances or in office, all the electrical appliances are connected in parallel connection. So in we know in the parallel voltage remains the same. So so here the voltage actually is the reference. We can draw the phasor diagram in a different way, like if you see the voltage here, and then this is the current, and this is the angle. So this is the theta actually. So just go back, so just theta. So it can be expressed as is a b 0 degree reference, and is the I, and there's a minus theta. So minus theta. So the both phasor diagram are same. Here's the voltage reference, here's the current reference, but everywhere in the both cases the current is lagging. So now just go down and go down. So here there's a clear phasor diagram here. So here voltage is the reference from this graph. Here's the just I draw the figure in the above. There is a node A and there is a neutral point for a single phase. So in the parallel there is a R and L. This is a XL reactive um, inductive reactance. So the total current is divided here, and where is the in a resistance? In earlier we say that there is a no phase difference between voltage and current, so phase difference theta is zero, and here we see that for pure inductive circuit it lags behind 90 degree. We know for capacitive circuit the current, for if there is a voltage and the in capacitive circuit IC, it should be 90 degree, but it must be in pure capacitive circuit. Okay, so and the resultant graph would be here in the middle of them. Then if we just make an expression like cos theta here, if you just draw the cos theta, then cos theta can be written as it's a horizontal component is IR by this one IAN. So IR can be expressed as IN cos theta. Okay, let's go down, and from the above expression, from the above expression, you see that if I just 2 cos A cos B, if we just apply the formula here, we get this one. Now you see that from the equation 1, the cos theta term, whatever the value of theta, uh, it's always positive. Cos theta is always positive regardless the sign. If the theta is negative or positive, it's always remain positive. So this is the peak value, then the average value can be expressed as this, and if we consider the RMS value, we know I RMS equal to Im root 2 over. So like Vmax can be written as a similar. So if I just put the expression, the IRMS, actually here I equals RMS value. So the RMS value is it's called a real power. It's called here, you see that it's called a real power, and the unit can be expressed as watt. So now we have to see the difference. What is real power? Later on I will discuss. So let me introduce the term of power factor. So it's typically mathematically expressed in cos theta, while the theta is equal to angle between voltage and current. So now see, in inductive circuit, in earlier I said that the inductive circuit the power factor is lagging. So current is lagging to the voltage, and in the capacitive circuit it's vice versa. So how this happen in the power factor? Because you see in the inductive circuit, I will show you another page for in sorry pencil. For inductive circuit, if I draw is a voltage reference, and then here current, and here is theta, here in polar form is 0, and here is angle minus theta. So what is the difference between these angle? Like Z, the impedance equal V by I, then it's a V angle 0 and I angle minus theta. It can be expressed as Z, and this is the phase difference between 0 minus theta. So it can be expressed as Z theta. So it's actually a positive value. So when the theta is positive for inductive circuit, theta You see that this is the angle difference between voltage and current. This is a voltage and the current. When the theta is positive, that is for expression in inductive circuit. So go back to this here. So I said over here, when the theta is positive, the current is lagging, and similarly when the theta is negative, for the capacitive, I mean the leading current. Okay, so now the second term of equation 1, go back to equation 1, and here is the equation. This is the sine part. So this is the sine, I mean the positive or negative value, the sensitive. So for the you see that the term here is sine theta. So for the positive value of theta, the sine theta is positive, and for negative value of theta, the sine theta is negative. So in the cycle, what I see in the cycle is positive and negative, and then average value is 0, and the term of sine, the sine expression is called as reactive power, that is VI sine theta. Then we get P equals VI is the real power. It can be expressed in watt, and Q is equal to reactive power. Here is called reactive power. The unit is volt ampere reactive, and then the apparent power, here is the apparent power equal to VI. If we just follow the Pythagoras rule here, then we can get the P square root over Q square equal to VI. So Q is negative for capacitive, since theta is negative for the capacitive, as I said in earlier, and Q is positive for inductive circuit, because sine theta, because Q is related to sine theta. So sine theta, the value of sine theta is related to the sine of theta. So the overall sine of Q actually depends on the circuit nature. So it's positive for inductive and negative for capacitive. Now let us see the expression and make the difference between the three different power, that is the real power, is the real power, is the reactive power, and the apparent power. So apparent power, actually it can called in a complex power. So it's there is a complex term is involved here. So in DC circuit, there is only resistive component is there. For example, incandescent life, where there is only a resistance inside as a tungsten, and for iron is just in the inside there is a resistance here, which is heated whenever we turn on the switch. So it's because of all resistance, because resistance absorbs power, and electrical energy is transferred into heat. But in AC circuit, the other two elements are involved with resistance, inductor and the capacitor. So we see that the current in the DC circuit, I mean the resistive circuit, is there is no phase difference, but in AC circuit there is a phase difference, because the current sometimes lag and sometimes lead. So this is why there is a complex thing is there. So we have to introduce here the complex power. So now let us see, here's the voltage and in this expression in polar form, and the current is here, and so the complex power can be expressed in the complex power is equal to expressing VI over conjugate. So conjugate sign is put over here. It means that I will show in the another page. So S equal to VI. So why conjugate sign is on top of the I? Because for example, in a complex part like Z equal to X J Y, so it's like X, so Y, so horizontal and the vertical component. If I put the conjugate here, then X minus JY. So there is no change in the real part. There is no change in the real part here. So only change is there is the x and is the y. So here why the question is why the conjugate sign is over I, because according to Ohm's law, I is proportional to B. That is a independent term and is a dependent term. So if it is dependent, then you see that here the x is independent in the horizontal axis, where so if I plot the graph here is I and it's a B. You just compare. I is equivalent to y, b is equivalent to x. So if I put conjugate over here, so there is no sign change. So the conjugate sign must be put in the vertical axis. Okay, so go back. Right, so conjugate sign, the sign is changed. So it's expressed in a exponential form, because we know that in phasor algebra, so z equal to x plus jy, it's a Cartesian or rectangular form. So it can be written as here theta, where z equal to x square y square and theta equal to tan inverse 1 y by x, and it's a polar form, and it can be expressed j e to the power j theta is the exponential form, and here another form is called cos theta j sin theta. So it's minus if I put minus over here. So it's a trigonometric form, it's an exponential form, it's a polar form, and it's a Cartesian form. So in phasor algebra we can express in different ways. So for the sake of mathematical simplicity here, let's see that there is a negative sign over here, and this is the angle between voltage and current. So we call it theta. So now the complex power can be expressed as Bi in the trigonometric form, as I showed in last slide. So it's a Bi, you can see it's a theta, it's cos theta, it's a theta, and the J is Bi sin theta. Here you see that the term is similar like x into jy, so it's a real independent term. So like P is the independent term, so this is why it's called a real power, and the q which depends on sine value sin theta, and the sine I mean the vertical component, because you see the sine always stays in the vertically, and the cos term is in the here cos term is in the horizontally. So now is we see that the reactive power is similar. Q is positive when the theta I mean the angle between voltage and current, because alpha is the angle for voltage, beta is the angle for current. So this is the power factor angle actually. So when theta is positive, because alpha is greater than beta, so that means the current is lagging, because we earlier saw that the theta is positive, theta is positive for lagging voltage, and the similar is one for the for capacitive circuit. Just go down. Now we see a power triangle here. See a power triangle. You see what is the expression is S equal to P and JQ. So here so P and the Q, and like Pythagoras there is a S, so we can write this S equal to P square Q square. So here for lagging power factor, the reactive power in the upward, because the theta is positive, and where is then the leading for the capacitive, and is the goes in the downward. So is the basic of power triangle. Similarly we can write for like J equal x plus jy, then this x y, this is z, and this is theta. Okay, now let's see an example. Let us see an example so that we can clarify the difference. So here it says that there is a voltage is 240 volt, AC voltage, single phase AC voltage, where Z, here is the Z is 10 angle 60, and we have to find the resistance and then reactance and then real power and reactive power and power factor as well. So what we can write here, like if we write J equal R plus JX, R plus JX, so uh, here you see that the angle is positive, so I can say definitely it's a reactive impedance. So if I draw the figure here, it's impedance, it's R, it's XL, and it's theta. Now here theta is given here, theta is 60, Z equal to 10 ohm. So now what is the cos theta? Cos theta can be written as R by Z. So here R equals Z into cos 60 degree. Here is a 5. Similarly, sin theta equal XL by Z. So it can be this, and the current is this. So P can be expressed as P equals B is here is just written I square R. The you can get the similar result if you put VI cos theta. Will get the same result over here because every value is known, and Q equal to the unit. You see the unit is a watt and this is a var, and it's we can put VI cos theta, and here power factor is just cos 60 degree. Just put a cos 60 degree, its value is half. It's because it's a power factor angle, because it's a Z angle theta. So in polar form, Z equal to Z theta is actually a power factor angle. So this is the theta. No need to do this, just follow this. It's a power factor angle. So we can easily understand this term power factor. So here is some more explanation over here. The same power triangle is shown here, and this figure and this figure is a power factor cos theta equal to, you see, this is R by Z and this is R by Z, resistance divided by impedance. So I will show you another example. So here it says the current is 10 and the voltage is 2, power factor 0.8 lagging. So what is the active power? Active power is VI cos theta, so it's in watts. So and the reactive power is VI sin theta is 100 is 1200 volt ampere reactive. So what is the apparent power? Apparent power is just is equal to VI, or if it is P and it is Q, then we can write according to above formula figure P square plus Q square, or we get the similar result. So here the unit is volt ampere. So here is the difference is that in DC circuit we can directly write P equals to VI. So we will get 2000 watt for DC circuit, but here we see that we can get 1600 watt for AC circuit. So why is the 400 watt? Because here is in the bar, inside the bar the power is just it's not a useful work, it's just a wastage. So this reactive power flows into and out, this is back and forth, so it's a loss power. So here is the difference in DC. This is why it's called apparent, because apparently we have to get 2000 watt, but instead of this we're getting 1600 watt because of this lagging power factor. If the power factor is unity, then P equals S, because P equals VI cos theta. So if it is 1, then we will get only VI, I mean the S. So this is the difference between DC power in DC circuit and the AC circuit. Now let's go. So here is another example. It's an inductive load, that means definitely a lagging power factor. It says the lagging power factor value is given cos theta equal to 0.6, and real power is 10 megawatt. And so draw the power triangle. If we want to draw the power triangle, what is should be here? P, Q and S. Here we have only P and this. So here is a theta. So cos theta equal P by S. Here we can find the value of S. Put the values over here. And then Q, I can get easily the value of Q, because Q can be written as Q equals to S square minus P square, and then put the value. I think we'll get this value. It's the higher reactive power in the inductive circuit. Now this is the power triangle for the first case. So now we see that determine the reactive power of a capacitor to be connected in parallel to the load. So here there is an inductive load. So here there is an inductive load. This is a load. If I add a capacitor in parallel here, so it is important to mention that if I add the capacitor in parallel with the inductive load, then the overall power factor will be improved, because the capacitive capacitor improves the power factor. So later on we will see in the power factor improvement section. Now it says that determine the reactive power in the capacitor. So you see that here says the capacitor is connected in parallel and the power factor is raised to 0.6 to 0.85. So similarly we have the value of P and cos theta equal to now 0.85, and do the math in the similar way and we can get this triangle. And so here in the first case we got 13.33 volt ampere reactive, and then we got 6.2. so what is the what is the reactive power improved by capacitor here? So just minus this and there is a improvement. And why there is a minus sign? Because as I said in earlier that Q is negative for the reactive value, because it just goes down. Though I am draw this figure here, so it could be like this. This is the negative sign, just ignore this, no problem with that. It should be S and Q. All that remains. This is a theta. Now power in balanced three-phase circuit. So it's a phase value for three-phase is 3, and for line value is can be expressed root 3, because we know that for Y connection BL equal to root 3 BP and IL equal to IP is for Y connection, and for delta connection for mesh connection BL and phase value and line value is same, but here's the difference is current. So if I put this value over here BP is a value, put the value of BP and IP, we'll get the this result whatever the connection. So and in reactive case this is the 3 VI sin theta, and similarly for line values can be written as this, and for apparent power like similar is root 3 V, and for phase value is 3 VI. That's all are similar one. So it's for three-phase circuit. Now I would like to introduce the operator A. So you see that in the j equal to x plus jy imaginary expression is just called a operator. So j can be expressed as 1 angle 90 degree in a counterclockwise difference. This is why there's x and this is y, actually it is jy, and here you see that it's a 90 degree and it's a anti-clock or counterclockwise direction. But why we have to introduce here the term a? So here you see that in three-phase circuit, so in a spherical there is a 360 degrees. So for three phase, each phase, if the number of phase equal to 3, then the contribution of each the difference between each phase should be 120 degree. So to express the three difference friends, we have to introduce the new operator called a can be expressed as 1 and the magnitude is 1 and the angle is 120 degree. The reference value is counterclockwise direction. The second one is 240 and the third one is another is just add 120 and you will get the just a similar one. This is the 3 after 360 the cycle will be remains the same. So now see the graph over here is the 1 and here is the 120. It's a 120, and if we go 120 more then we'll get a square, and then if I move another 120 then I will get once again a cube or a square. So it's a simple. So for introducing the reason behind the introducing of a is the for representing the three phase in a mathematically in a phasor. Now let us see the most important per unit component. So per unit value can be expressed as actual quantity by base quantity. So here is our one formula, and here there is a base impedance. There is another formula of this is another formula of base impedance. Here it's just a simple math over here. So base voltage kV square by MVA, or it can be written as kVA given the volt ampere, and the it's a line to neutral. So it can be used for three phase, is for single phase. So in three phase it should be line to line, but the formula remains same. Okay, just go down. So show an example here. We see that there is a rated rated MVA. There's a apparent power is given because all the generator and the transformer is typically given in MVA, because whenever the device manufacturer build this device, that time the power factor of the load is not known. So this is why it's rated in voltage and ampere, and when the load is connected then we will get the theta. Okay, so here's the line voltage is given here, and the per unit value is over here. So we have to find the ohmic value, I mean the actual value. So we know per unit equal ohmic, I mean actual base. First of all we have this value, it's 1.1, and base value, base can be impedance, base can be expressed as go up. So kV square MVA. So here is kV is 12 kV, and then MVA is 500 MVA. So just put the formula over here and then here, and we'll get the ohmic value. And note that if there is a more component in the same circuit diagram, in a single line diagram, I will talk about later about the single line diagram, then we have to follow another new formula. Here is the per unit given value, given I mean the value will be given in the question, and the new value I mean the base value. For example, we have to think a base. So why we need to introduce the per unit component? Because per unit component we see the we know in the power system element we use different kind of device like generator, transformer, and then the different type of load, switch gear. So every circuit breaker, every element are in a different rating. Some rating can be expressed, for example, some rating in expressed in current. For circuit breaker it can take a certain value of current, and generator and transformer is usually rated in kVA or MVA, and the transmission line voltage can be expressed in voltage. So all of the different unit associated in the same figure. So to express all the component and the same unit, we use to per unit expression. So it's just like a normalized value. So we have to consider reference base value, and then if we just divide the actual value, we get the lower value. So in base value, you see the value would be higher. So if there is another two more than two or three components, so the expression can be written as. So here is to show the example. uh, Here the reactance of a generator designated X double prime, actually it's called a subtransient reactance. If it is X prime, then it's called a transient reactance, and if just there is only X, it will be called or synchronous or steady state reactance. So it's a part of steady state operation of generator. So it's a given value, that is the per unit given value is 0.25. Here the given value 0.25 per unit value, and all the unit is per unit. All the unit can be expressed in per unit. And here you see the given value. You see given 18, given 18 in the, and here is the given value is 500. Here is the given is 500, and the base, here you see that there is a base value. Base value actually means the new value in the formula. So base value, you can put here the base value is 100 over here, and the base value new is 20 over here, and we'll get the per unit value. So this is the process of getting the new per unit value for more than two component. Now we'll see the single line diagram or one line diagram here. So from in our power system, so there is a four different section, from generation, and then transmission, and then distribution, and then we are in the load side where the consumer, that is in the utilization section. So there is a four different section actually, and the course name this ELG4125 is doing actually accordingly. So what is the purpose of single line diagram? So in single line diagram, all the elements from the generation to the load end can be expressed in one line in a single line diagram. So all the component can be explained and the significant information in a concise, in a short form about the entire system. So here you see that it's bus 1, it's bus 2, bus, I mean this is a common connection where all the units, all the generating or the transformer unit is a common point. Normally it's made of copper bar. So is typically called infinite bus. Infinite bus means it can take any number of generator. Normally in the power station there could be a more than one generator. Here the round shape means the machine, I mean it could be a generator or the motor. So it's a generator, and this is the circuit breaker. There is another generator, and the neutral is connected via reactance and resistance. So there is a specific reason behind this. I will not discuss in this lecture. So there is another there is a load is connected in the generating station, and then a step up transformer, because typically the generating end voltage is lower, is a value around 11 kilovolt, and the transmission, this is the step up transformer. This is the step up, actually it's a power transformer. It's actually a three phase transformer. It's the first transformer, and the circuit breaker is connected in the both side. And here it is the transmission line, and here is the another transformer for step down to for the purpose of using the load, because for example, if it is 230 kilovolt, we are not using this voltage. For single phase value, the line voltage is 400 volt, or we or 230 phase volt, whatever. So here is the it is the step down transformer, and here there is another load is connected over here, and there is another generator also connected for just a example purpose. So if we show the simplified reactance diagram over here, we see that go up, go up. So here's the neutral connection. We have to draw the neutral one first, and then here you see that machine 1 is here, and the reactance, there's the equivalent reactance is here, machine 2 the equivalent reactance, and we do not need to show the load because the only concise information on the important information is shown over here. No need to show load or the circuit breaker or the current transformer, potential transformer. We do not need to show this component over here. And this is the equivalent for transformer reactance, and this is for transmission line, and this is for transformer 2, and this is for generator 3. So it's the simplified diagram. So in that's it. Okay, go down. So generation of electrical energy, as we know in earlier in the machine, electrical machine device. So in the actually the generator is called a synchronous generator or called alternator, and there is a three phase here, red, yellow, blue, and there is another point is a neutral. It should be in black, is black or green color for three phase. So prime mover actually is a mechanical device. It's run by steam or fuel or nuclear or anything else energy from source. That's just run the prime mover. It could be it's like a motor, and it's run the rotor of this alternator and then produce the electrical energy there. So it's a basic of generation electrical energy. So now we will see the unit of electrical unit. So it normally one unit as electricity bill, one unit can be expressed in 1 kilowatt hour. So here is 1 kilowatt hour. 1 kilowatt 1 hour can be expressed in this mechanical energy. If we express in joule, it can be expressed in mechanical energy, but in electricity bill we must have to express in kilowatt hour. Whatever the power is, could be watt or megawatt or gigawatt, but always expressed in kilowatt hour. So here we see that is a load curve over 24-hour duration. So is a, you see in the evening time there is a peak load over here. So what is the demand, or you can say the power generation? We just you see the energy can be expressed. Here is the power, here is the time. If you multiply this, you will get watt into hour. So you have to express in kilowatt hour. So the area under this load curve is actually the unit, I mean the energy generated or energy consumed over 24 hours, from the midnight to noon, 24 hours. So there is another graph. There's some power station that is actually using for base load, that is run all the time over there, and there's some generating station acting as a peak power peak station. So it's only start when the peak demand. Okay, so it actually depends on the design criteria. Now I will discuss the power factor improvement. So as I said earlier, if there is a voltage and there is an inductive load over here, this is the load, and the current is and the voltage here. So here I must be lagging. So if I just draw the diagram over here, this V is the reference. As I said, in the parallel, all the voltage normally can be used as a reference value. So it's a reference, and then the I should be this lagging. The big angle is a phi 1 here, and if we just now add the capacitor in parallel with the load, then if it's considered the pure capacitor, then the IC would be here, and the resultant of IC and I should be in between of these. So it must not cross over here because it's not the leading nature, so it's only the leading. So you see that now the power factor angle is reduced to phi 2, so cos phi 1 and cos phi 2. So phi 1 is greater than phi 2. So here, so the cos theta 1 should be less than cos phi 2. That is, the when the angle is lower, the power factor is improved, because you see that I prime, the resultant current here, is moving to the V. If it reaches to here, then theta equals 0. So it would be like as a resistive circuit, so power factor will be 1 in that case. So this is the improvement. What is the improvement? This part is the power factor improvement, and this is done by adding a capacitor in parallel with load. Now here is see an example. An alternator is supplying 300 kilowatt. P value is given. I just draw the power triangle here. It's a kVA, VA, or okay, just erase the VA, and it's a watt, and it's a var. So here is a 300 kilowatt is given here. Power factor 0.6, cos theta is 0.6, and if the if the power factor is increased to unity, so 0.6 to 1, then how much power can deliver the alternator supply for the same kVA loading? So first of all, find out the kVA is 500 kVA for 0.6. so in kilowatt 0.6, what is the value? 300 kilowatt power it can give. So whenever the power is increased to unity power factor, so similarly you can put the value over here. Just similar the same formula, cos theta value is now 1, and kVA rating for the same kVA rating, the value would be 500, and then the power would be 500 kilowatt. So here 0.6, the given power is 300 by alternator, but whenever the power factor improved to 1, is this it can give more output power, so 500. So additional power it can give 200 kilowatt hour. So it's the improvement. Now I will show you the power system scenario, typical power system. So here is the generating station, and then there is a step up transformer. There's a, you see that it's typically 11 kilovolt. So there's a particular reason behind this, because it's consuming the natural resource, the source of energy. So non-renewable energy could be coal, or natural gas, or is fuel, furnace oil, or high speed diesel, or fuel, or and it could be nuclear. So if is the size is bigger than the natural than the resource, the raw materials would be higher, so it will burn more, and the reserve will goes down. So typically it keep in 11 kilovolt, and then this is the three-phase step up transformer, 220 kilovolt. So there is a particular reason behind the high voltage transmission line, because there is a low voltage drop. We see that P equals VI, so I equals P by V. So if V is higher, then I is lower, and therefore the I square R, the transmission loss I square R would be lower because it's a square value, so it's been reduced lower. So this is the benefit of high voltage. This is the high voltage transmission because the power is low, power loss is low. And then the primary transmission, and once again there is another drop here. So either it's 220 to 132 or 66 is a secondary transmission. Some people call it distribution because some high load industry load can be taken directly from the 66 kilovolt line, depends on their load size. uh, okay, so and then goes down. This is the distribution substation, is 11 kilovolt to the, this is the end consumer, this is the line voltage, and this is the phase voltage, this is the end user. So we are using just a single phase, but for the higher value they can take it from the 11 kilovolt line directly, or 66 kilovolt line directly, as depends on their load demand. So now here you see that there is a percentage of line drop for the higher value of the line drop is lower. For if the voltage is higher, the line drop is lower because it is inversely proportional. Now I would like to discuss a little bit about the transmission line. So there is a three type of transmission line. One is short transmission line, two is medium, and then a long transmission line. So for the short transmission line, the basic circuit diagram can be expressed as here. This is the sending in voltage, that means from the generating station. This is the load end, that's the, is called the receiving end, and is the transmission line impedance. Okay, and if I see the phasor diagram over here, we can draw it another way, like if the voltage is the reference, then current, and for R it will follow the current fashion as I said earlier, and then it will go up IXL, and according to equation you'll just is Vs, because Vs can be written as Ij into Ij plus Br. So Ij can be written as IRJXL. So adding all the value, I can get this sending in voltage. So here is the receiving in voltage, is the power factor angle between voltage and current, is the I. This is the receiving in current. This is the in series circuit, the current remains same. So here this is the all. So it's a voltage regulation. So voltage regulation, I mean the voltage regulation is actually you see from the equation Vs minus Vr equal Ij. So actually it's a voltage drop over here. So it can be expressed is a voltage drop divided by Vr. So voltage drop, so our expectation is the voltage regulation should be always there, because we want to find the low drop over here, because we want to send all the voltage in the load end. So the transmission efficiency can be expressed by receiving in power divided by sending in power, or the receiving in power plus the loss associated over here, that means the Br cos theta plus I square R. As I said earlier, I square R is the, here is the C, I square R is the transmission loss. And the voltage regulation, here is the sending in voltage expression, and here is the just put this Vs minus Vr, you will get this equation. The for lagging power factor, this equation, and for leading there should be minus over here. And this is the medium transmission line. It's just a pie shape, is just a pie shape. Is the admittance over here is connected on the two side for the compensation purpose. It's a pie shape, and sending in voltage equation is there, and the sending in current, and in generally it can be expressed this. So A, B, C, D are the transmission line constant. So and now I will talk about the switch gear. talk about the switch gear element. So in switch gear uh, is used for switching, controlling, and the protecting. So now the protecting device is come here. So isolator is just but a single switch, so it can be operated in the under no load condition. So it's typically connected before and after the circuit breaker. So here is just see the diagram of circuit breaker. Here there is a transmission line. Current transformer is sense the high current transformer actually is used also. There is actually a instrument transformer. So two type of instrument transformer, one is current transformer, another is a potential transformer. So potential transformer measure the voltage because there is a in transmission line high voltage line, so we can't measure in normal way like using a multimeter. So we have to put a current transformer because it's a ratio. For example, if the ratio I1 I2, if the ratio is 0.5, then if the 0.5, for example, if the original value is actual kilo ampere, then we if 0.5 means actually it's flowing 50 kilo ampere current. So the current transformer just measure the whatever the transformation ratio is set over here. Similarly for the potential transformer, however, the current is flowing here. So when the fault occur, I mean the short circuit happen, the current transformer detect the fault current here and then send the information to relay coil, and then relay inform the trip coil. The circuit will be closed and the trip coil will inform the circuit breaker over here, and then the circuit breaker will open accordingly. So for the safety of the load. So it's the principle. So there is a basic difference between fuse and the circuit breaker. Circuit breaker is for high rating device, and whereas a fuse is nothing but a wire, it's just a resistance. So whenever the just electricity is flow, so if the range is crossed, then it's just melt out, and the device, then the load inside is safe. So here a fuse can identify the fault and isolate the load from the line. And but in here, and for circuit breaker can't detect the fault current. So fault current detected by the relay coil through the current transformer, and its job is circuit breaker job is to just isolate. So it can only isolate, not identify. So it's a basic difference. The circuit breaker here is just show the single bus system. Here you see there's a generator, is a single bus over here, and a circuit. Here you see the circuit breaker. So in the here the isolator is connected over here, because isolator for the maintenance of circuit breaker, if we need to replace, we have to just open this one and then this one. So it's for additional safety. And yeah, so circuit actually the isolator never be open until the circuit breaker in the same circuit has been opened, and should always be closed before the circuit breaker is closed. And so now I would discuss the problem for our first DGD. So here is the problem is given, the figure is given. This is a three phase circuit. So we have to find out we have to draw the per phase equivalent diagram. So here we see the diagram first. So here is the generating unit. This is a generator 480 volt, and there is a step up transformer. You see that 482 to 13.8 kilovolt. So definitely it's a step up transformer. SKV rating is given, and the resistance and reactance, the per unit value is already given, and then it's the transmission line. So its actual impedance is given over here, and this transformer is actually step down. You see here is a 13.8 kilovolt, and then step down to 480 volt, and the kVA rating is just half of that. And here two type of load is connected. It's not that is theta is positive, that definitely it's a inductive load. And here you see that ZL is a negative value, that means it's definitely a capacitive load. So two different load connected in parallel through a switch. So there is a different scenario question is over here. So now the region is divided into three regions. So just before the transformer and between the two transformer and the transmission line, region 2, and the load section after the transformer, the load section is divided is specified as a region 3, and the all value are is given here. So now it's time to solve all the value in per unit per unit value. Now let us see we have to set a base impedance first. So if we consider for reason 1, it's a base apparent power is a base value for base kVA is base kVA is 1000 kVA, and the base voltage is 480 volt here. So similarly we can took the base value over here for the reason 2 and reason 3 no matter what. So for this example we consider the base value of that, so accordingly we have to change this reason also base value. So I have to find the base impedance first, and then we'll draw the diagram. So basic impedance, the formula is given here. So you see that it's a phase value for phase 1. So the equation I showed in earlier, so J base can be written as kV square on 1000 divided by kVA. So kV square, I mean, so kV square for here is 0.48 kV here, and 1000, and then kVA value is 1000. If I put this value, you will get this one, or you can done this way. Here is can be done with, as we know, is I mean the kVA equal to for three-phase circuit, and earlier show the three-phase circuit BP IP phase value, and then 3 Vp I equal to V by Z. So it's actually base, then I can write Z equal 3 V square. So base value actually V square divided by S means kVA. So here you see that the formula is same. So we can do the same way, but remember that here the voltage value is put 277, but here it is shown 480, because what we have to do is a phase value so phase value can be written as VL bug root over 3. Here you see there is a line value, so his line value is 480 divided by root 3, we'll get 270. And similarly for this all case, go down. So it's a base value in the three reason 1 2 3, and then the per unit value is already given for transformer 1. Go up here is the per unit value for the transformer section, and transformer 2 the per unit value is already given 0.1 0.01 and 0.04 yeah. So now we have to find over the reason 2 here. So if we said in earlier, if we have more than one component, so there is a more here is a generator element, one transformer, two transformers, a transmission line. So we have to follow that formula that I showed in earlier. So accordingly to, so it could be either find resistance or reactance or Z, whatever the expression for. So for the all expression we use the same value. So accordingly this value, so we can just put over here, like for transformer T2 is, see that the given value is 0.02 is here, and here the according to this value per unit this 0.02, and the V base 1 by base 2. Base 1 in earlier we took it 1000 1000 is a 1000, and then base 2 is 500. You see that here the V base 2 is 500, and the voltage is you see that the base 1 voltage is uh, just a 7967. I mean the if you divide the 13.8, I mean 13,800 divided by root 3, will get 7967. Just put the value over here and we'll get this value, this for R2 and this for X2. And now we have to find all the per unit of all elements. So we already get T1 value is over here, T2 we just find. Now we have to find the for the transmission line. Here you see that the actual value is given here. So for the transmission line, for the transmission line, what is the formula? I said in earlier, per unit value equal, sorry, per unit value equal actual by base value. So here is the actual value is 1.5 J10, 1.5 J10, and the base value, so it's fall in the region 2. So in the region 2, what is the base value? Let's see, base value is 190.4, in the region 2 is 190.4, is 190.4. We'll get the part, this is the all the per unit value. Now we have to go in for load. Here load is Z and this is the theta is given. Then the for load 1, what is the, is the actual value, and the what is the per unit value. The same formula is like this. So in the load remains in the region 3, what is the base value for the region 3 is 0.238, as 0.238. So here we use the 0.238, and for the load 2 it's also in the region 3, and it's the given value is 0.833. Go over there, given value is 0.833 minus actually it's a capacitive load, and the value is that. Now it's time to draw the equivalent diagram. So it's for generator. For generator, you see that there is a one. Why? Because and the given value go up, it's a given value is 480, actual value is 480, and here we choose a 480 for base. So according to formula per unit equal to actual is 480, and the base we choose 480, so it's 1 and 0 degrees for the reference value. And then according to the given figure, now transformer, then transmission line, then transformer 2, and then load. Okay, now draw the figure. This is the transformer, we already get the above, and then this transmission line, and the transformer 2, and the load, Now let's go to the next part. When the switch is open, that means for figure for the question B, when the switch is open, so it's just open, is not considered in the circuit. So then the overall impedance, what will be the overall impedance? Just add this, and this, and you will get this. What will be the current? I equal V by Z total. So Z total is the current. And what would be the load voltage? Load voltage is in per unit, V equal IZ. So Z is here and I is here. I actually, if just Cartesian value is the both are equivalent, it's actually the same. Here is the polar form, here is the rectangular form, and if you multiply this, we'll get this. So what would be the actual value? Actual value is the actual load voltage. What is the load voltage? The formula is same. Formula is the per unit equal actual divided base. So per unit value, we got the per unit value. Actual value, what is the actual value? It's a actual value is just a base into per unit. So base value, we assume assume in the base value is the base value is 48, and the actual value is 0.494. So you will get actual equal per unit multiply base. So this sorry, not this, not this, this is this. Okay. Now, what is the power supply? Power supply is just I square R. Just I square R. The value is I is here 0.4325. What is the value of R load? R load go up 1.68. R load here. Here's the for load 1. Here's the R, and here is the X. So it's a 1 series of the load is load power supply I square R. And if I just uh, find the actual value, we have just multiply these, because this is watt, multiply this is by 1000, because the base value, like the same formula, like the same base value we considered here 100 in the first. Let go f once again. Here is the base value, voltage base value 480, and the base value of kVA apparent power is 1000 kVA. So if I just base into per unit, we'll get the base base into per unit, we'll always get the actual value, is the actual value. And the power supplied can be expressed as VI cos theta. So cos theta is just we'll get in the load section. Theta, why is theta? Theta is 36.87 degree. So we know the value of theta. So just put it there. Here the angle should be here. The angle should be here. This is the 41.2 degree, and this is the per unit value is of V into I. We know the value of V, and why it is V is this one, and I is 4.4235. So if I this is the all are per unit value, so if I multiply 1000 kVA to all of them, then we'll get the actual value, all of this actual value. If I just multiply the base value. Okay, now the power factor is just cos theta. Theta's value is here, it's a lagging. Now let's go to the part C. When the switch is closed, the equivalent circuit, go over the circuit. This one is, if it is closed, then these two load in parallel. So what we can written here, if it is Z1, if it is Z2, then Z1 Z2 divided, so multiply Z1 plus Z2, and sum of all of this series connection. So here is the multiply thing is there. Now what would be the current? I equal V by Z. This is the Z total. This is the current. What is the load voltage? Similarly, like I to Z load. And look, here's the load. Z load is a different value, 2.267 J10. So it's a load. Now the load is the two parallel load. So one for Z1 and another for capacitive load Z2. So this value is come from this value. If we just multiply this, we'll get this one. So this is the load and this is the actual value, just like as before. And here is R load. How can we get this? R value is 0.2672. Here is a C, just load is a R, and this is X, just I square R, the load transfer. Power supply to the load, because it's always in I square R, and the actual value can be given by just multiply base value with the per unit values. Similarly as before, like the power delivered VI cos theta, reactive power VI sin theta, and all, and multiply by 1000 kVA with this per unit value, we will get the actual value. And the power factor is here is the angle, here is the angle. Power factor is 0.995. So note it is noticeable that when the switch was open, you see that the power factor, the switch was open here, switch was open. This is the inductive load, this is the capacitive load. So when the switch open, no capacitive load is connected to the system. So for the inductive load, let's see the power factor. Where is the power factor? Power factor here, power factor is a 0.752 lagging, but when the switch is closed, I mean the capacitive load is connected to the parallel of the inductive load, and you see the power factor is, what is the power factor, is 995, and here 0.752. So the power factor is getting improved when we add the capacitor in parallel with the load. And now in this last section, what is about the losses, transmission line losses. So losses can be expressed in I square R, in similar I square R, but it in the transmission line losses, so it must be considered in the transmission line. So here the transmission line losses, when the switch is open, switch is open, I means the load 2 is not connected to the load, then I square. So go back to I in the first case, on the, because you see when the switch is open, then what is the value of I, 0.35, and what is the and the value of R, what is the value? This is the transmission line, this is the R, and this is the X. So R value is 0.0078, go down, I value 0.4325, this is the 0.4325 square, and this is the R, and we'll get this, and this is the actual value, just multiply by 1000. And when the switch are closed, then when the switch is closed, this switch is closed, then the current value is 0.371, and the R remains, transmission line R remains the same. So go down, and this is the yeah, this is the I square 0.371, 0.371 is here, and 0.371 is here, and the R values remains same, I square R, and the similarly we will get the answer. So yeah, you see that the load 2, this is the capacitive load, definitely improve the power system, because the power system improvement can be done by adding capacitor in parallel. Also there is another two-way, just adding a synchronous condenser and the synchronous motor in the overexcited condition. So yeah, so it's a basic, that's a common basic, is that if we add the capacitive load in parallel with the inductive load, then the power factor will be definitely improve. So far we have learned here the drawing the equivalent circuit diagram. So it's just a single line diagram, because from the generation there is a transmission, there is a distribution, because transmission means the conversion of high voltage, and then once again the step down the voltage, and the load is over here. So it's a single line diagram. So here is the generation, is the transmission, is the distribution, it's the utilization is here, and we now learn how to find the per unit value and draw the per phase equivalent diagram. And we also know that the power factor improvement as well. So I think it's a complete package, I hope. So thank you, sir. So this is all about from my part. Have a good day. Assalamu alaikum.